Yeah.
Great. So I thank you for being part of the conference today. I would now hand it over to the chair of the session, Sangeeta, to take forward this session.
Thank you, Sayanti. It feels great to be part of this 24-hour conference, and thanks for inviting me to be the chair for this session. And without further ado, I want to introduce our speaker for the next 30 minutes, Nahid Sultana. Thanks for joining us. A quick introduction about the speaker. Nahid Sultana is a PhD student, and she's also a lecturer at Sharjah University of Science and Technology. Her PhD is on methods for estimating relative treatment effects with single-arm studies. And today we have a really interesting topic. So she's going to present on a simulation study to explore the effects of repeated use of individual patient data in a MAIC-adjusted network meta-analysis. So, like in the recent days, even, in our colleagues are really, doing a lot of MAIC analysis. So I'm really interested for the talk. So, I'm not going to take much time. Thank you so much for joining. Please, the stage is yours.
Thank you. Okay, let me share the screen. I hope you can see the slide now.
Yes.
Okay. Good evening, everyone. So I'm Nahid Sultana. I am currently working as an assistant professor in Sharjah University, Bangladesh. Now I'm doing my PhD in University of Sheffield. I'm last year PhD student. I'm in my final year. So yeah, so as the chair says, the topic of my PhD is basically on single-arm studies and to explore the methods which can be used to estimate relative treatment effects with single-arm studies. So this simulation study is a part of my PhD. So I will first try to give you a background of how I get the motivation or encouragement to do this simulation. So as all of you know that the gold standard in estimating relative treatment effects is considered to be a randomized control trial or RCT. RCT guarantee a high level of unbiased assessment of efficacy of treatment due to the fact that randomization makes it obvious that the groups in the treatment and control group, the patient will be as similar as possible with respect to patient characteristics. So the confounder variables are balanced using this randomization procedure. And at the end of an RCT, when the output or outcome are compared, the clinicians are quite obvious that the difference in result comes from the difference in treatment, not because of any kind of confounding factors. So in a RCT, we are able to do treatment comparison in head-to-head trials. But this is not the case for an indirect treatment comparison. As you can see in this figure, there are two kinds of indirect treatment comparison has been depicted. Let us suppose that treatment A and C need to be compared, but there is no head-to-head comparison available between them, which has been depicted by this broken line. But in the first figure, between treatment A and C, there is a common comparator, which is B, which is not present for this second figure. So in this kind of situation where we have to make treatment comparison between treatment A and C, and there is no head-to-head comparison available, but there is a common comparator treatment is available, we can use this common comparator treatment and we can preserve the randomization between studies. So in this kind of indirect comparison is termed as anchored comparison. And the advantage of this kind of comparison is that the prognostic variables can be balanced between studies due to the use of this common comparator. So only the effect modifier variables need to be balanced between studies. But in figure 2, as you can see, there is no common comparator exist between studies. Both prognostic as well as effect modifier variables need to be balanced between study to get a valid relative treatment effects. And this kind of situation often occurs in practice with single arm studies. For example, let us suppose that this treatment A comes from a single arm study. So let me just give you a brief explanation about single arm study. Single arm studies are comprising of prospective series of patients all receive the same treatment. There are various reasons that people are doing single arm studies. Maybe there are unprompted improvement in patient is not expected, or placebo effects are very minimal, or there can be assigning patient to a placebo arm is unethical. So in those kind of situations, people or clinicians are doing single arm studies. And in health technology assessment, there is again another complexity with single arm studies is that the company which is conducting the single arm studies, they have individual patient data for their own study, but they don't have access to IPD for the comparator study. They only have aggregate data available for the comparator study. So in this kind of situation, when we don't have access to IPD for all the studies, we can't really apply the methods of regression adjustment or propensity score matching to balance out the covariate between studies. So we need to go for a next step to how to deal with this kind of partial availability of IPD data. So nowadays, population adjustment methods like MAIC or STC are quite popular to balance out this kind of imbalance between study to get a valid relative treatment effects. Valid relative treatment effects, yes. So this slide shows us just a quick overview of the method I'm going to talk about. It's called matching adjusted indirect comparison, or in short MAIC. And this picture shows us what it is doing to balance out the covariate. So as you can see, a indirect comparison needs to be made between A and C, as there is no direct comparison exist between them. And the covariate severity of patients is also imbalanced between the two arm of the treatment A and C. So in a MAIC, a weighting procedure is applied using a logistic regression, which ultimately balance out the patient characteristic between studies, and the weight is applied in the final analysis to get a weighted relative treatment effects. So in addition to the limited availability of IPD, when I was doing a review in my first year of PhD, we also came to realize that in health technology assessment, it is often the case that a single arm study need to be compared with multiple comparators. It could be that a single arm study need to be compared with multiple comparator from multiple studies, as it is shown in the first figure, or it can be happen that a single arm study need to be compared with a single comparator, but all these comparators are coming from different studies. So in both of these cases, the company have to deal with a disconnected larger network of evidence. And in those situations, it has been found that in some of the technical appraisal document, it was found that some of the companies are implementing the MAIC or STC multiple times using the IPD of the single arm studies several times. And all these MAIC estimates, they are assuming that the MAIC estimates made a set of coherent relative effect estimates without assuming the transitivity of these estimates. And they are using these MAIC estimates in a NMA settings to get relative treatment effect for multiple treatment. So they want to make treatment comparison in simultaneously so that they can compare multiple treatment in one single setting. So this was the motivation for the simulation study. I wanted to see what is the impact of using the IPD from a single arm study repeatedly, because it breaks the independency of the unit of analysis. Also, what is the consequence of using the MAIC in a NMA settings? So in order to see all of these consequences of MAIC in a larger disconnected network of evidence, we formulated a simulation study, and this figure shows the data generation mechanism for the simulation study. In total, four data was generated in 4 settings. First, a small and large connected network was simulated and a connected network meta-analysis was conducted. So what I mean by small and large connected network is that it means the number of studies available for per comparison. So in a small network, the number of studies was 3, and in a large network, the number of study was 10. So after generating a connected network, the network was artificially converted to a disconnected network, and then MAIC was applied in those network, and then a NMA was conducted. So the NMA which was conducted using the MAIC estimate was termed as a MAIC-adjusted NMA. So this figure again shows us the steps of the data generation. So the first figure is what I was talking about. It shows how the smaller network was simulated. So in the smaller network, there were 3 studies. 2 studies contribute to 2 RCT between treatment 1 and 2, and 1 RCT between treatment 1 and 3. Similarly, in the larger network, 6 studies were simulated for treatment 1 and 2, and 4 studies for treatment 1 and 3. And this figure, it shows how the MAIC estimates was used, how the MAIC estimates was extracted and used in an NMA. So in the first figure, as you can see, there was 3 RCT was simulated for the connected network. And after simulating this connected network from each RCT, 1 treatment arm was dropped to make every RCT into a single arm study. And after making every RCT into a single arm study, the MAIC was applied, which has been shown with these arrow figures. So after implementing the MAIC multiple times, the MAIC estimates were implemented in a NMA settings to get the relative treatment effects for treatment 2 and treatment 3. So in the simulation, the following factors was varied, which was overall sample size, correlation coefficient between covariates, the effect modification strength, prognostic variable strength, overlap between study covariate. And the whole simulation was conducted in a full factorial design, which resulted in 32 scenarios. And the simulation was conducted by satisfying the shared effect modifier assumption. So this assumption assumes that the competing treatments belong to the same class, and all the studies are sharing the same effect modifiers. So this table shows us that the different scenarios. So the rows with the red colors, these are the scenarios with high overlap scenarios, and the black ones is with low overlap scenarios. So the estimate of interest in this study was the overall treatment effect estimates from the connected NMA and the overall treatment effect estimates from the MAIC-adjusted NMA. The MAIC-adjusted fixed as well as a random effect NMA was performed. Robust standard errors was estimated from the NMA estimates. And bias, empirical standard error, model standard error, and coverage probability was estimated as a performance measure. So I'll start now the result. So this is the result for the fixed effect NMA with the smaller network of evidence. So this figure shows us the amount of bias by overlap, which shows us that bias and overlap was related. Higher biases was found for low overlap scenarios, and lower biases was found for high overlap scenarios. So this figure is for bias by overlap with effect modifier. So higher biases were found most of the time for higher effect modifier levels. This shows higher biases was found for low prognostic variable levels. And this is the coverage for treatment 2 for different sample sizes and overlap. So the black line shows us the nominal level of coverage, which is 95%. And it shows us that for the high overlap scenarios, for all the scenarios, the treatment effects were as at nominal level, that is at 95% level. But with low overlap scenarios, there was slightly decreased seen for the coverage. This figure is for treatment 2. Again, for the high overlap scenarios, the coverage was at nominal level, but with low overlap scenarios, for some cases, there was slightly reduction was seen for coverage probability. These are the results for the fixed effect NMA with a larger network. So as I shown previously, the bias was related with overlap. High biases was seen with low overlap scenarios. Higher biases was seen with high effect modifier levels and high prognostic variable levels. And this is the coverage for treatment 2 for varying sample size and overlap. So as for the smaller network of evidence, we could see the coverage was at nominal level for higher overlap scenarios, but with the larger network of evidence, under coverage was seen for every data generation mechanism. So all the scenarios, in all the scenarios, the coverage probability was below 95%. And this was true for treatment 3 also. These are the results for the random effect NMA with a smaller network. As before, higher biases was found for low overlap scenarios, higher biases with high effect modifier levels and high prognostic variable levels. And for the coverage probability, again, the coverage was at nominal level for high overlap scenarios, but there was a slight drop for the low overlap scenarios. Again, this was true for treatment 3. And these are the results for random effect NMA with the larger network. Bias was like before, higher biases with low overlap scenarios, higher biases with higher effect modifier levels and higher prognostic variable levels. And again, the coverage was under coverage was seen for every DGM or every scenarios for both treatment 2 and treatment 3. So as a conclusion, we could say that the main impact of implementing MAIC in a larger disconnected network of evidence using single arm studies was seen for the coverage. So under coverage was seen for each data generating mechanism, and the under coverage was more pronounced for the larger disconnected network of evidence. Bias and overlaps were found to be inversely related. The general trend was low bias with low effect modifier levels and low prognostic variable levels. And the magnitude of biases was found to be lower for the larger disconnected network. Under coverage was slightly better for the random effect NMA model. So the main problem with this NMA was found for the coverage probabilities, and due to the fact that robust standard error was estimated, so the robust standard error was not able to capture the variability completely, which was the reason that we couldn't reach to the nominal level of coverage. So to get a solution for this problem, instead of using robust standard error, we have used bootstrapping, and not any conventional bootstrapping. We have used double bootstrapping. So this figure shows us how we have done this double bootstrapping to solve this problem of undercoverage issue. So during the step when the MAIC was estimated, as in the larger disconnected network of evidence, I have calculated 9 MAIC. So in this process of calculating the MAIC, we were using the IPD from the single arm study multiple times. So instead of using the IPD from the single arm study, we have bootstrapped this IPD twice. And then the bootstrap sample are used in estimating each and every MAIC. And then all these MAIC are implemented in a NMA to get the relative treatment effects. So after implementing this double bootstrapping with MAIC estimates, the under coverage issue can be overcome, and all the DGM was at nominal level. thank you everyone for listening. And if you have any question, I'm happy to answer.
Thank you, Nahid. Audience, if you have any questions, you can type it in the chat box and we can take it from there. Yeah, in the meantime, I have one question, Nahid. So, when we take different studies to get the comparator, how much of a standardization issue was there? Like each study would have different kinds of data standardization, right? So was there, like any kind of standardization issue that we encountered, or how did you go about that?
Sorry if I have understood your question correctly. Do you mean during the data generation process, is there any kind of standardization that
Yeah.
So, okay, so basically, the data generation was done for binary data, and no, I don't think I have made any kind of standardization. It was simple generating binary data using in a RCT setting.
Okay. Yeah, got it. Yeah, thanks, Nahid. We don't have any other open questions. Any other questions? Yeah. All right, then we can wrap this session 5 minutes early. Yeah, and give Sayanthi time to breathe. Thanks, Nahid. Thanks for joining. Thanks for presenting. Yeah.
Thanks to you also.
Thank you so much for being part of the celebration. Many thanks to both of you, Nahid and Sangeeta, and hope you enjoy the rest of the conference.